So we're now on to part 1.8, simulating data to improve your research. And we're going to do a bit more simulation, this time of multivariate data. We're going to look at the program called Simulation X2A Correlations, which you should have downloaded off Open Science Framework. And this allows you to simulate a situation where you've got multiple variables of interest rather than just one dependent variable. And the script will show you how to use a function called MVR norm or multivariate normal, which is part of the mass package, which you should have already installed in an earlier exercise. This also demonstrates the dangers of p-hacking, I think, quite nicely. So I'll just come out of PowerPoint and look at my script up here, and we'll just step through it again. So we'll start by loading these packages and disabling scientific notation. You may know these grid extra and grid you may need to install. If you remember that, you do that by going to tools, install packages, and then selecting these two. They are solely there to allow me to format the output to make it easy to see what's going on. They are fairly horrendous to use, and I don't expect you to be able to follow the script where this is done, because it's really complicated, but just take this bit on trust, because it does help clarify otherwise what's going on. So we're going to try and simulate 7 variables. You could change this. So I went for 7 largely because it's easy to fit on the screen. And we need to use this multivariate normal function. If you want to understand a function, you can just do help and then the name of the function. But as I said before, sometimes the official help information from R is a bit too technical and unfriendly, and it's often better to just Google something, Google MVR norm, and you'll find lots of advice on how to use it. In order to simulate multivariate normal data, you need to know 3 things. You need to know how many values you want to simulate, which is just the sample size, n, how many variables you want to simulate, each of which will have a mean. So mu is actually a vector of means for the variables you're simulating. And then you need to know the relationship between the different variables that you're specifying. That is how far they're correlated with each other. There are other arguments which we don't need to worry about. If we use z-scores, we have the advantage that we've always got a standard deviation of 1. That really makes life a lot easier in many ways. For a start, it means that the variance, which is the standard deviation squared, is also 1. So if we want to make a covariance matrix showing the relationships between variables, we can just put 1 on the diagonals. So what we do here is we set our number of variables to 7, and then we can use this rep command to just create a little vector of 7, or however many variables we specified with nvar, zeros. So if we go here, let's do this here. We're setting various values, and we will down here, yeah, the rep actually is down here when we get to MVR norm, which we'll come to, but you're just saying you repeat the value you've specified for my m, which is actually 0, for the number of variables. So if I were to do, for example, rep 0.7, you just get a vector of 7 zeros. So that's more or less what we're going to be doing. This is just making a little vector that's going to hold all the p-values that we're creating. And we're setting the number of simulated data sets to 5. If you're doing serious simulations, you're often talking about thousands of simulations, but to just understand how the script works, you just pick a small number here. And this is a counter that looks at how many significant p-values you've got in a given run. Now, the difficult thing with this is, or the most complicated thing is this correlation, this matrix or covariance matrix that you need to specify. Most people know about correlations and are less familiar with covariances. Depends how you've been trained, I guess. But the correlation coefficient we know goes from -1 to +1, and that's a positive correlation. That's a negative correlation. And then if there's no correlation, it's 0. The relationship with the covariance is simply that the correlation is the covariance divided by the product of the standard deviations of the two measures of interest. So we have actually got a standard deviation specified of 1 and 1 for our two measures, all our measures. So in this case, the correlation coefficient and the covariance are the same, which is one reason we're using z-scores. It simplifies this. So if we've got a z-score and we've got a correlation of 0.5, the covariance is also 0.5. You can have covariances, if you're not using z-scores, they can be on almost any scale that you've specified. So they're not like the correlation, they're not naturally bounded. Anyway, what we're looking for is to create a table rather like this, because this is specifying the covariance in each of these between the two variables of interest. And I've put them all at 0. So we're simulating null data where there's absolutely nothing going on. These variables have no relationship to one another. But you can use MVR norm, of course, and put different values in here. You could put in a correlation of 0.3 or could vary from one variable to the next. Now, to create this little matrix, we start off just making a matrix of all zeros and then stick ones on the diagonals. So, and again, you could change the off-diagonal values if you wanted to, but what we do here is we make this thing called Mykov, and that's just repeating whatever we've set as the correlation, which is in this case 0, and we need to have a matrix 7 by 7 in this case, with arranged in 7 rows. So Mykov is all zeros to start out with, and then we put on the diagonal, we just put ones or whatever value you've selected. But in this case, we're working with correlations, it's all going to be ones. So we end up with this little matrix, which is what I showed you in the slide. And that is what multivariate normal simulation will draw on when it's simulating data. It wants them to have those relationships. They're drawing from a population where there's no correlation between off-diagonal members and the variance of 1 for those that are with themselves. So that's a variance of a variable with itself. And I put here, before you start, let's just go back to our simulation up here. Before you start, it's a good idea to clear everything. And remember, we have our little broom here. You can clear and say, yes, get rid of everything. And I might want to clear this console with Control L. Nice clean start. And I'm suggesting that we skip over the line here to start with on up here. We're just going to go to my data, which is created with this command. So that we should have now enough to, I haven't specified my M, beg your pardon. That's because I cleared everything, of course. Right, go back and rerun this. All up to here. Yes, I can't shut down the device because it's not got anything in it. That's a command that just clears this plotting space. So it's telling me it can't clear it because there's nothing on it. That's not a big problem. But now we make my data. And you can see we've made this nice array of 30 rows of 7 variables, which are designed to are drawn from this population with these particular characteristics. If we look at the actual correlations, we've got my result. They're a bit bunched up here, but there you are. You see that there's quite a lot of correlations that are not 0 here. And you might think, well, why is that? I've told them they should be 0, but this comes back to this question that we had before of the difference between a sample and a population. If you draw a sample of only 30 from a population, you'll find that there's variability in that sample. It's not going to be exactly the same as a population. We can then look at the, let's see what I'm saying here. We run the lines of the script and we look at the data and see the first 6 rows, what they look like. And you'll get a fresh set of numbers on each run, although you can do something called setting a seed if you want to keep the same numbers on each run. Now you can analyze your simulated data and look at the correlations between the 7 variables. And I suggest you can pick your favorite variables. Maybe you might think, well, there's going to be a correlation between variables 1 and 2 or 5 and 7. And then you have to anticipate. This is the interesting thing where the simulation may challenge what you anticipate you'll get. Do you think you'll get, if you simulate data, will you get typically no significant correlations, some significant correlations, or something specifically between the 2 variables that you're interested in? I think most of us would agree that this last one is perhaps not terribly likely. But let's see what you actually get. So I'm now going to run just the whole program. And it should put up a little, woo, it's not got quite enough space to put it up. Sometimes, yes, it pauses a bit. This is this weird table thing. And so we've got a load of correlations here, and it's not showing anything of interest because I've set it up so that if there's anything that's conventionally p less than 0.05, it will show up in red. So we didn't get anything on that occasion. So let's try running it again. I might need to clear it first in order. This table thing is actually quite, let's get rid of that first and then run it again. There we are. This time we've got 2. We've got one of 0.38 and one of minus 0.37. But the point I want to stress when I said pick your favorite 2 variables is you can see these things that are supposedly significant, but they can be anywhere. And they're not the same from one run to the next. Let's run it again. Probably won't show it again because this is a bit, yeah, there we go. So this time there's nothing. And we're just sort of hopping through. Yeah, sorry, I do need to, this is a very temperamental package, this table one, and you tend to have to clear everything before you run it or it gets overloaded. Now we've got one over there. Basically, what I did in the slides here, just to save us having to go through this painfully slowly, is show you some typical output, which is very similar to what you're seeing there on the screen. So you get these odd red things popping up, but they can be all over the place. And there's one there where you could get 6 significant correlations, and we know that there's really nothing going on. So what's happening? Is there something wrong with R? Is there something wrong with multivariate normal? The answer is no. It's simply that this is part of variation in small samples, output of similar, and it's not just the small samples, it's the fact that you've got a large number of correlations that you're looking at in any one run. So on any one run, you're looking at 21 correlations. So what we should be taking into account is that because we're looking at so many correlations, we should be operating with a more stringent p-value, 0.05 divided by 21, if we really want to work with a 5% probability of a type 1 error. And that means we would have a much larger value of R, 0.51, that we would be taking as so-called significant. And when you look at these simulations I've done, then if you take that value, you would find only 1 in 20 simulations would be coming up with a significant result on that basis. So that would be correct. That would be, the p-value would then be meaningful in the way that it should be. I think the best thing is at this point, if you try and work through the script yourself, you can run it to generate your own table of results. So it will be simulating many times, but to save, again, to stop your pain of results getting overloaded, it's just trying to print out the last one. And I recommend you do clear it before you run it each time, because otherwise it can sometimes just fail to produce that nice little plot. Don't worry if you don't understand the bits of the script for generating tables. It's a nightmare, and it's something I just pulled off the web. It's extremely complex coding, but the most important thing is that you should just develop competence to play around with the script and change things like the sample size, the number of variables, and the true correlation between the variables, and see how far does that actually influence the sort of patterns of results that you get. And at that point, I think I'll just leave you to play with it, and then we can come back and discuss something else.